Hello students, I am Ma'am Nayad and for today we will be discussing Quarter 2 Module 6 which is all about mirrors. But before anything else, let's review our previous lesson about electromagnetic waves to get our brains warmed up. Question number 1. What electromagnetic wave is the second lowest frequency wave in the EM spectrum? Radio waves, gamma ray, microwaves, or infrared waves? Very good. The correct answer is microwaves. Question number 2. What part of the electromagnetic spectrum is visible to the human eye? Ultraviolet waves, visible light, X-ray, or gamma rays? The correct answer is visible light. Number 3. What EM wave is used for night vision and comes in handy for security cameras? Infrared waves, radio waves, visible light, or microwaves? Very good. The correct answer is infrared waves. Question number 4. What electromagnetic waves can cause sunburn and even cancer in living organisms? Microwave, gamma rays, ultraviolet, or X-rays? The correct answer is ultraviolet. Question number 5. What EM waves are commonly used in imaging technology to view bone structures within the body? Microwave, gamma rays, X-rays, or radio waves? Alright, the correct answer is X-rays. Very good. Now that our review of the electromagnetic is clear, let's zoom in one specific EM wave that is critical to our lesson today. Visible light is the essential agent that allows us to see the world around us. And more importantly, for today's module, it's what allows us to see our own reflection. Our most essential competency for this discussion would be to predict the qualitative characteristics of images formed by plane mirrors, curved mirrors, and lenses. When we say qualitative characteristics, it refers to the orientation, type, and magnification. But for our lesson for today, we are just going to focus on discussing the plane mirror and curved mirrors. Now, what is optics? Optics is the branch of physics that studies the behavior and properties of light, including its interaction with matter and instruments used to detect it. And today, we are going to discover how light behaves in plane mirrors. For today's lesson, I want you to become explorer and discover how the mirror works. I provided 4 activities, and this activity is entitled Mirror, Mirror on the Wall. For task 1, on a clean paper, write the capital letter A. Show it in front of the mirror and write how the letter appeared in the mirror. For the second task, at the back of the same paper, assuming it is clean, write the capital letter E this time. Again, show it in front of the mirror, write how the letter appeared in the mirror. And then for the third task, using the front of the paper, where you write the capital letter A, write the word ambulance in all capital letters. Show it in front of the mirror and write how the word exactly appeared in the mirror. Then for the last task, copy your answer in number 3 on a separate paper and then show it in front of the mirror. Then write how it appears in the mirror this time. Now I will give you 3 minutes to accomplish your activity and make sure to write your answer in your science notebook or in a separate sheet of paper. For task 1, what changes do you observe in the letter A from left side to the right side? When you look at the reflection of the capital letter A, you'll notice it looks exactly the same as the original letter. And this is what we call as symmetry. It is when a shape can be folded in half and the two halves are exactly the same. The line of symmetry is the line that divides the shape into two identical halves. The letter A is unique because it is vertically symmetrical. If you draw a line straight down the middle of the letter A, or what we know as a vertical line of symmetry, the left side is a perfect match for the right side. The mirror performs a horizontal flip, wherein it swaps left and right. Because the left and the right sides of A are identical, swapping them still results in the original and recognizable letter A. And aside from letter A, we also have different letters being considered as symmetrical letters. Letter A, H, I, M, O, T, U, V, W, X. Let's quickly analyze task 2, which is the capital letter E. When you held up the letter E, what did you write down? You should have observed that the letter E was clearly flipped. Baligtad. Unlike the symmetrical letter A from task 1, the E has no side-to-side symmetry. The vertical bar, which was on the left of your paper, appeared on the right side of the image in the mirror, and it looks like this one. This horizontal reversal, where the left of the object becomes the right of the image and the right becomes the left, is a critical property of reflection. We call this phenomenon lateral inversion. And this letter E is considered as asymmetrical letters, wherein these letters do not have a vertical line of symmetry and are flipped horizontally in a mirror image. We have different letters under asymmetrical letters such as letter B, C, D, E, F, G, J, K, L, N, P, Q, R, S, and letter Z. Let's look at task 3, which brought the letter flipping to a full word, ambulance. When you wrote the word ambulance on your paper and held it up to the mirror, you saw the entire word was reversed horizontally. The letter A at the end was now on the left, and the letter A at the beginning was now on the right. This again is the work of lateral inversion. The mirror simply swaps on the left and right positions of everything it reflects. Again, this process is known as lateral inversion. And now for the final twist. For task 4, I ask you to take the word you copied in task 3, which was already backwards, and hold it up to the mirror. So, you held up a paper that looked like this. What did you write down for how it appeared in the mirror this time? You should have found that the word looked perfectly normal. It was readable left to right, AMBULANCE, and being read as ambulance. So let's answer our real world question. Why is ambulance written backwards on the front of the vehicle? Which of the two statements would explain why the word ambulance in ambulance cars is written in a reversed manner? Explain your answer. Letter A. The word ambulance in ambulance cars, which are emergency vehicles, is written in reverse so that the drivers of any vehicles in front of it can instantly read the word correctly in their rear view mirror, since the images formed in mirrors are reversed. Thus, they can give way for the ambulance right away. Or letter B, The word ambulance in ambulance cars, which are emergency vehicles, is written in reverse because this can make the drivers in front of the ambulance see the word clearly so they can give way immediately. So the correct answer is letter A. The word ambulance in ambulance car is written that way so that a driver who sees the ambulance approaching quickly in their rearview mirror, which is itself a mirror, will have the image laterally inverted back to the correct reading order. This allows them to read the word instantly and move out of the way, saving crucial time. And this is the main reason why the word ambulance in ambulance cars is written in a reverse manner. Again, this process is known as lateral inversion. In the previous activity, you successfully completed the four activities from the symmetrical letter A, flipped letter E, to the tricky double burst or reversed ambulance. We saw the result the image was laterally inverted, but what is the action that created the image in the first place? At its most basic, this process is known as reflection. Reflection is defined as the bouncing of light rays when it hits a surface like a mirror. And it looks like a ball bouncing whenever it hits the surface, just like the image on the right side. We just defined reflection as the action or the bouncing of light. Now let's define the object that performs this action so perfectly, the mirror. Reflection can also be seen using a piece of glass, car side mirrors, or even a calm body of water. Your mirror is designed to be highly reflective, ensuring that almost all the light that hits it is perfectly bounced back to your eyes, allowing you to see a clear, sharp image like this one. Yes, a mirror is also considered as a wave reflector because it reflects waves, most commonly light, but also other forms of electromagnetic radiation like radio and infrared rays, through a process called specular reflection. Now that we know what a mirror is, let's look at the different types of mirror, starting with the one you use every day, which is the plane mirror. In its most basic form, a mirror is a flat piece of glass coated with a highly reflective metal. Because the reflective surface is perfectly flat, we call it plane mirror. Plane mirrors are the most common type and are found in your bathrooms, bedrooms, and department store dressing rooms. The image they produce is always same size as the object and appears to be located behind the mirror. The second type of mirror is known as spherical mirrors. These are mirrors which have the shape of a piece cut out of spherical surface, and think of them as curved mirrors. Because they are curved, they give us two distinct types, each with its own special use: the concave mirror and a convex mirror. A concave mirror curves inward like the inside of a spoon, while a convex mirror curves outward like the back of a spoon. To analyze how light behaves on mirrors, let us familiarize ourselves with five different reflection vocabulary terms. First, we have light ray. A light ray is simply our idealized model of light, which we always draw as a straight line with an arrow showing its direction of travel. Next, when drawing a reflection, we have the incident ray, and this is the ray of light that is approaching to the surface of the mirror. It is the light coming in. After the reflection happens, We have the reflected ray, and this is the ray of light which leaves the surface of the mirror, and it is the light bouncing off. The most important term for measuring reflection is the normal line, and this is an imaginary line that we always draw perpendicular, meaning at a 90-degree angle to the surface of the mirror, exactly where the incident ray strikes. And this line is our baseline for the all angle measurements. Now for the angles, in math, the Greek letter theta is the most commonly used to represent an angle. The angle of incidence is denoted as theta and small letter I. It is the angle measured between the incident ray and the normal line, and this tells us the angle at which the light is arriving. And finally, the angle of reflection, which is denoted as theta and a small letter r. It is the angle measured between the reflected ray and the normal line. This tells us the angle at which the light is leaving. Take a moment to look at this diagram. All of these terms are connected, and they are the language we need to define the fundamental rule of light, which is the law of reflection. Let's discover what is stated in the law of reflection. Let's break down the two rules within the law of reflection. Understanding these rules is the key to drawing any ray diagram. Statement 1. The same plane rule. This statement says that the incident ray, the reflected ray, and the normal line must all lie on the same plane. What does same plane mean? Imagine your mirror is lying flat on your desk. If the light ray comes in horizontally across the desk, it won't suddenly jump up and bounce toward the ceiling. It stays contained in the same two-dimensional space, and this rule simply confirms that light travels in a predictable, straight line and doesn't curve into three dimensions unexpectedly when it reflects. Now for the statement 2, the angle equality. This is the most crucial part. It states that the angle of incidence is exactly equal to the angle of reflection. This is a hard rule for any smooth surface. For example, the angle of incidence is 50 degrees, meaning the light arrives 50 degrees away from the normal line, and the angle of reflection must also be 50 degrees as it bounces away. This law is why mirrors are so predictable. This is why you always know exactly where your image will appear when you look into a mirror. The light bounces off the mirror surface with perfect mathematical precision. With this law defined, we can now start building ray diagrams for our plane mirrors. We have defined the law of reflection. Now, let's put that second statement to the test with a simple question. What is the angle of reflection if the angle of incidence is 45 degrees? The answer is 45 degrees. If you got that right, you have understood the most important rule of reflection. Remember, for any smooth surface, the angle at which the light ray arrives is always exactly equal to the angle at which the light ray leaves, and that is known as the law of reflection. The angle of incidence is equal to the angle of reflection. This time, let's try to solve this problem number 1. Find the angle of reflection and the angles A and B. Always remember, in the law of reflection, it is stated that the angle of incidence, the yellow one, is always equal to the angle of reflection. And the given is 35 degrees, meaning the angle of incidence in this diagram is 35 degrees. Now we are asked to solve the value for the angle of reflection and angles A and B. Since the angle of incidence is always equal to the angle of refraction, therefore, the angle of reflection is also 35 degrees. Now, how about angle A and letter B? Now, try to recall the previous lessons in your math subject. If you will notice, the normal line, the angle of incidence, and the angle of reflection is perpendicular to one another. When we say perpendicular, the angle is at a right angle or 90 degrees. Now let us solve the value for angle A. Angle A plus 35 degrees is equal to 90 degrees. Angle A again, angle A plus 35 is equal to 90 degrees. Now to solve the value for angle A is equal to 90 degrees minus 35 degrees. Therefore, the answer is the value for angle A is 55 degrees. Similarly, the value of angle B is also 55 degrees. So this time, you are going to solve problem number 2. Find the angle of incidence, angle of reflection, and angle A. And do not forget to apply the law of reflection, wherein the angle of incidence is always equal to the angle of reflection. Again, the angle of incidence and angle of reflection were positioned perpendicularly to one another. Therefore, 50 degrees plus theta I, or angle of incidence, is equal to 90 degrees. Now, let's try to solve the values for theta I, theta R, and angle A. 50 degrees plus theta I is equal to 90 degrees. The angle of incidence is equal to 90 degrees minus 50 degrees. Therefore, the answer is 40 degrees. Again, the value of our angle of incidence is 40 degrees. Now, what do you think is the value of our angle of reflection? The value of our angle of reflection is also 40 degrees because in the law of reflection, it is stated that the angle of incidence is equal to the angle of reflection. How about angle A? Again, for problem number 2, the value of our angle of incidence is 40 degrees. Therefore, the value of our angle of reflection is also 40 degrees. Now, how about angle A? Yes, you're right. Since our value here is 50 degrees, therefore, the remaining angle here on angle A is also 50 degrees. Since you are now familiar with the two statements under the law of reflection, now, can you tell me the difference and similarities of picture A and picture B? These are images of Mayon volcano which perfectly demonstrate the difference between specular and diffuse light interaction. The core difference is based on how the light is scattered by the surface and the atmosphere. Image A. This appearance is a result of a specular or regular reflection. This happens when light rays reflect off a smooth surface or pass through a very clear medium without scattering. The result is a sharp, distinct image with high contrast, making the volcano look clear and detailed. Now, how about image B? This appearance is dominated by diffuse reflection. This occurs when light hits a rough surface like volcanic rock or thick atmospheric haze or clouds and scatters in many directions. This scattering softens the image, reduces contrast, and can make the volcano look like silhouette or shadow, as the light isn't reflected clearly back to the camera. Specular images result from light reflecting of a smooth surface like a mirror, where rays bounce off in the same direction and form a clear, sharp image. This is known as a specular reflection, wherein the angle of incident ray is equal to the angle of reflected ray. Diffuse reflection, on the other hand, are images created by light scattering of a rough surface, such as paper or clothing, where ray bounces off in many different directions and do not form a sharp single image. In diffuse reflection, the angle of incident ray is not equal to the angle of reflected ray. Now that light rays are bouncing off the mirror according to the law of reflection, the result of that bounce is the image we see. But not all images are created equal. There are two distinct types of images in optics: virtual and real. Let's start with the virtual image. A virtual image occurs where the reflected light rays only appear to diverge or spread out from a point behind the because the rays only appear to come from the image location and don't actually meet there. You cannot capture a virtual image on a screen. Critically, a virtual image is always upright and right side up, and this is the type of image produced by all plane mirrors. Now let's look at the real image. A real image is formed when the reflected rays actually converge or meet in front of the mirror. Reflected rays actually converge or meet in front of the mirror because the light rays genuinely meet. You can capture a real image on a screen. However, a real image is always inverted and upside down. These images are produced only by certain types of spherical mirrors, like the concave mirror. So the main difference is simple. Virtual means the light only pretends to form the image behind the mirror and it is upright. Real means the light actually forms the image in front of the mirror and the image is inverted. Now we can understand the characteristics of the image formed by the simplest mirror of all, which is the plane mirror. We just discovered that plane mirrors produce virtual images. Now let's list the other key characteristics and look into your own plane mirror or imagine one in front of you. Let's try to answer these 4 questions. Question 1. What is the orientation of the image? Is it upright or inverted? Does your head appear at the bottom of the mirror, or is the image right side up? The correct orientation is upright. The image is always right side up. Question number 2. What type of image was formed? A real image or a virtual image? Remember, can you catch it on a screen? The image formed is a virtual image. because the light rays only appear to diverge from behind the mirror and cannot be projected. Question number 3. Compare the size or height of the image to the object. Is the image larger, same size, or smaller? The size is always same size as the object. A plane mirror never magnifies or shrinks what you see. Question number 4. If you are 3 boxes away from the plane mirror, how far is your image from the mirror? The image is also 3 boxes away or same distance. This means the object distance is equal to the image distance. The image is always as far behind the mirror as the object is in front of it. Again, in the previous activity, the images formed by plane mirrors is upright, and the image is upright, therefore, it is virtual. The size height of the image is the same as to you or the object, and the image has the same distance to you or to the object from the mirror, which is also 3 boxes. Always remember, the image formed by plane mirrors is always upright, which means it is a virtual image. A plane mirror produces image that has an apparent left to right reversal, like the image being shown on the right side. The image and object are the same distance from a plane mirror. The image, size, height is the same as the object size of the magnification is always equal to 1. And to summarize our lesson for today, always remember the acronym LOST. L for location, O for orientation, S for size, and T for type of image. The images formed by plane mirrors is virtual, erect or upright, same size as the object. The image distance is always equal to the object distance, and it is laterally inverted. Now I want you to answer the 2 questions under the formative assessment. Prepare a piece of paper and ballpen. Question number 1. Study the image below. What is the value of x? A. The value of x is 30 degrees. B. It is 30 degrees because the angle of incidence is equal to the angle of reflection. C. The angle of reflection is 30 degrees because the angle of incidence is always equal to the angle of reflection that lies in a normal line. Or letter D. The angle is 30 degrees because it is perpendicular to one another. The correct answer is letter C. The angle of reflection is 30 degrees because the angle of incidence is equal to the angle of reflection that lies in a normal line. Question number 2. Study the image formed by a plane mirror. What is the nature of image formed by plane mirrors? A. The size of the image is the same with the size of the object. B. The image is laterally inverted with the same size of the object. C. The distance of the image and size is the same with the object's distance and size but inverted. Or letter D. The image is formed in front of the mirror. The correct answer is letter B. The image is laterally inverted with the same size of the object.